Today we're going to tackle two problems that relates to the integrated rate law. In our first example here, we're given an equation. We're told that 80 grams of this reactant decomposes to 2.5 grams, and we're asked how much time did it take. So then we would use the integrated rate law, but which one would we choose? That would depend on our reaction order, which we can pull from our rate constant. It's S to the -1, so that's actually a first order reaction. So the integrated rate law that we would use would look like this. Now we know that in our equation it asks for the concentration, but we're given the mass. So what we do is first we'll just isolate for the time because that's what we're being asked for. Okay. Actually, I'll just put K, just keep it here on this side for now. So how you go about this is, we know that concentration is equal to N divided by V, mole divided by volume. And since N is equal to mass divided by molar mass, so what ends up happening is molar mass and volume on the top and on the bottom will cancel out, because in this scenario, the molar mass and the volume is constant. So what you end up getting would look like in ln, and then you would just put the mass at the time that you're interested in over the initial mass. That would equal to our T, where we also divide it by our K. So what we end up getting is 5.6 times 10 to 3 seconds. That's a time it takes to decompose from mass 1 to mass 2. And we see how we can use the concentration of the integrated rate law to apply it into masses as well. That's a big takeaway. But the second problem, part 2, is how many liters of O2 is produced? Given that this is a gas, we'll use the ideal gas law, PV equals nRT. But in order to find the liters, we'll need to find how many moles there are as well. So, how many moles? So what we need to do here is make this statement. Understand what we had for here. So the time it took to decompose from 80 to 2.5 grams is around 5,600. So at that many seconds, after that many seconds, there is 2.5 grams left. So that means the difference between these two numbers is the number of grams that actually reacted this way to form the products. So what we need to do is, instead of just using our stoichiometry, we have to understand that the mass or the number of moles we're going to use for this reactant here is going to be 80 minus 2.5 grams. Which is 77.5 grams. This is the amount of mass, this is a mass that actually reacted to form the product. So this would be the mass that you would base off your stoichiometry with. And then obviously we would convert it into moles. Mass divided by moles, molar mass, that gets you moles. And then just afterwards, it's pretty simple. Once you get number of moles, you want to find the moles of oxygen, which according to stoichiometry should be half. And this will get you the moles of oxygen. And then you can just insert the rest of the equation into this equation. There's nothing else fancy left, so I'll just give you the answer. So the big takeaways, I chose these two examples because they're sneaky in two ways. The first is you're given the masses, although the equation wants concentration, but you're given the masses. So what you can do is use this so that you can still work with the masses you're given to find the time it takes to reach a concentration. So this is the relationship between mass and concentration in integrated rate laws. And the sneaky part about this one is when you have an equation and you're asked how many liters are produced, your reactant should be based off of what you have actually reacted. So that's the difference between the initial to the final mass or moles. But it is not just the final moles. You see how it might be easy to just think, okay, I'm going to base on my stoichiometry based on 2.5 grams. But no, that 2.5 grams is how much that's remaining. That's not how much reacted. So for this takeaway, I would say difference. Difference of reactant initial minus final gives you amount reacted to form products. So this amount would be the actual amount to use to do your stoichiometry. And now, just to test if you learned what I just talked about, let's say you're given this hypothetical equation and you're given these two information about the rate constant and the initial concentration of A. The question asks, what is the concentration of B after this many seconds? So we know that the concentration of B after this many seconds would be, first of all, we're given the time, so we want to find how much concentration is left at this time of A, because we're given the initial concentration of A. So this tells us that we have a zero order reaction. So a zero order reaction, integrated rate law, would look like this. And then if we just sub the things in, we'll find out that the concentration of A at this time is around 7.5 times 10 to the negative 4. So then this concentration is a concentration that's remaining. But what's remaining isn't what has reacted to get our B. So to find the amount of A that reacted to get B, we would need to take away this amount from our initial concentration, which tells us that only 2.5 times 10 to the negative 4 moles per liter actually reacted of A to form our products B. So the concentration of B would be based on this amount times the stoichiometry. Here is just 1/1. So that now the concentration of B then would be the same, since it's timing 1 by 1. And so there you have it.